general equilibrium, the topics or the concepts behind this topic, and what are the possible calculation problems that we should expect. Okay, so this is one of the basics that we have to understand in analytical chemistry. Okay, so before we go deep into the topic, let's go back first to the chemical reaction. Okay, so in chemical reactions, we usually have our reactants reacting all together to form your products. Okay, so that's the idea for chemical reactions. Reactants are combining, decomposing, or whatever they want to do to form the products. Okay, so that's the usual idea. However, for systems that is in equilibrium, okay, something quite weird is happening because some of your products are going back to your reactant stage. Okay, so that means if a molecule that turned into this molecule will go back to this. Okay, so that's the idea. So that means we have a dynamic process. When I say dynamic process, that is a two-way process. A process going to the product side and a process going to the reactant side. If two reactions are happening at the same time in a given system, we call that chemical equilibrium. Okay, so chemical equilibrium is a state in which a system is having an equal tendency of forward and reverse reaction. Okay, the rates of the reaction are equal. So we have a forward reaction that is towards product, and we have a reverse reaction. This is towards reactants. And two reactions are happening at the same time. If that happens, we are in a chemical equilibrium. Okay, so usually chemical equilibriums are denoted by this double-headed arrow. The first arrow at the top indicates that the reaction is going to the product side. The arrow at the bottom part indicates you that reaction is going to the reactant side. Okay, so what do we have to take note? For equilibrium systems, two reactions are happening, forward and reverse reaction. Okay, so what's equal is that the rates of those reactions are equal. Okay, only the rates, not the concentration. Okay, so for us to describe the equilibrium system, we usually use a number, which is the ratio of the concentrations of your products and reactants. We call that the equilibrium constant. Okay, so equilibrium constant is a way to describe your system by the ratio of the amounts of products over the reactants. So suppose we have this general equilibrium expression where A capital letters A, B, C, and D are your substances, and small letters A, B, C, and D are stoichiometric coefficients. When I say stoichiometric coefficients, these are numbers that are used to balance the whole equation. Okay, so to write the equilibrium expression for this reaction, we write K is equals to the concentration of your products over the reactants. Okay, so to write the concentration of your products, we use square brackets. Okay, square brackets indicate, this is a square bracket. Square bracket indicates the concentration. So we use square brackets instead. Okay, so that's the square bracket of substance C. Why C? Because C is in the product side. Okay, so that's the concentration of C raised to the stoichiometric coefficient of C, the small letter C, times the concentration of your substance D. raised to the stoichiometric coefficients, all divided by your substances in the reactant side. Now, so that is the concentration of A raised to A, concentration of B raised to B. So that's the idea. Okay. We have two types of equilibrium constant. The first one is expressed in concentration. We call that Kc. This is the equilibrium. So we have two types of equilibrium constant. Kc, this is in terms of the concentration, and Kp, this is in terms of pressure, and this applies for gases only. Okay, so we have two types of equilibrium constant, the Kc and the Kp. What we have written here is in terms of concentration, so that is Kc actually. Okay, so what if we're going to write the Kp equivalent equation for this one? So suppose that all these species are gaseous species. Okay, so if you want to write the equilibrium um, expression in terms of pressure, this is still the same, products over reactants. However, if we use the square bracket, that is exclusively for concentration units. Okay, so since we are talking about pressure here, we will not use the square bracket. Instead, we will use a capital letter P. Capital letter P indicates that the unit of concentration, or the unit of amount of the substance, is in terms of pressures. Okay, so to write the Kp expression for that reaction, that is just the pressure of substance C raised to the stoichiometric coefficient, pressure of substance D raised to the coefficient, all over the pressure of substance A raised to A times the pressure of substance B raised to B. Okay, so indicate that they are the same, they are similar rather. Okay, so they are similar, however, what only changes is that for Kc we use square brackets. For Kp we use this letter P. We indicate pressure. Okay, so again, so equilibrium constants, these are numbers that obtains the ratio of your products and the reactant concentration, and we use this to describe our equilibrium system. Okay, so what else do we have to remember? For equilibrium constant, only substances in the aqueous and gaseous space are to be written. Okay, so only aqueous systems and gaseous substances are to be written. So how about solids and liquids? We're not going to write them. Okay, so the rule is no solids and no liquids in K. So we're not going to write solids and liquids in the equilibrium constant. Okay, so suppose we have this equation. Okay, so let's write the equilibrium constant. Okay, so since all the phases of this reaction is in aqueous spaces, we will only have Kc for this expression. Okay, so Kc is products over reactants concentration, because that is in aqueous spaces. Okay, so for the product side, we have concentration of H plus times the concentration of OH divided by K. So according to the rule, only substances in aqueous and gaseous spaces are to be included. That means no solids and no liquids. So are we going to write this? So the answer is no. we're not going to write H2O liquid. Okay, so that means the Kc for this reaction is just the product of H plus times the OH minus. Okay, so this is the answer for that question. Okay, so above this one, so we have here a reaction in the gaseous phase. Okay, so we have N2O4 in equilibrium with 2 NO2 all in the gaseous phase. So how are we going to write the equilibrium constant for this? Okay, this is just a tip. Okay, note, if your substance is in aqueous phases, you can write Kc only, no Kp. However, if your substance is in the gaseous phases, you can write Kc and Kp. Okay, so that means to write the equilibrium constant for this expression, for this reaction, we have to write Kc and Kp. How are we going to do that? Okay, so for Kc, that is the concentration of your product over reactant. So that means Kc is equals to the concentration of NO2 raised to 2. Why do we have a 2 here? Because the reaction, or the NO2, has a stoichiometric coefficient of 2. Okay, for the reactant side, we have N2O4 raised to 1, Y1. If nothing is written here, that is automatically understood as a coefficient equal to 1. Okay, so that is the Kc expression for this reaction. How about the Kp? Okay, so for Kp, that is the pressure of product or the pressure of reactant. So that means Kp is equals to the pressure of NO2 raised to 2 over the pressure of N2O4 let's raise to 1. Okay, you may not write that. Okay, so just to show you that the coefficients are to be written as exponents in the expression, so I place the 1 there, but you may not do this anyway. Anything raised to 1 is just the number itself. Okay, so that's how we write equilibrium constants for gases. Okay, again, if your substances is only in the equation if your substances is only in the aqueous phases, all you have is just Kc. If your substances is in the gas phase, you both have Kc and Kp. Take note of that. Okay, so